Okay, good. Let's go to the new network and we learn new stuff. We have a new system, common source amplifier, still common source amplifier, right? Let's again tell ourselves what we are doing here. This is gate, this is drain, this is source. What we did is add an RF, feedback resistor. We do have RC, we still have a CF, right? But now it is small. We assume we can ignore it, right? In the real circuit simulation, you will take into account. But we deliberately put an RF here. We bias this one with a current source, right? With constant bias. So PMOS, VGS, W on L mu C ox divided by 2 VGS minus VT squared. That is the current going out. It is in saturation. This is just like a current source. Of course, it's not an ideal current source, but we bias it, and it has certain output impedance, right? I can also just model it as this, RO0. Its output impedance is RO2, RO2, the output impedance of a transistor, right? So we bias it, and then this is a small signal model, small signals input. That's what we care about. It has a source, output impedance is an output impedance, and we couple it with this capacitor to couple this signal to here. You cannot just connect them together, right? Because this might be 1 volt, and then you cannot add a plus minus 0.2 volt to 1 volt if you don't have the capacitor, right? Because you're going to short it. But with a capacitor, the DC part is separated, but the AC part don't see the capacitor. You just go through, right? So we did not have time to talk this, but I think I spent a lot of time in E122 to talk about the meaning of small signal and DC bias, right? We talk about why we need this coupling, right? So now just take it for granted. And then here draws the small signal model. Now somehow we here assume R20 is very large. So we ignore it. And because this is current source, in small signal, what do? Open it. You open it. Then you only have RO2. And now I assume RO2 is large. Then just like open it. So everything is gone before the V out. And here we short this resistor, right? Now, actually they did not. We should also draw RS, but we can do that later. Yeah. So now what is the R in? The question is R in. We ignore channel length modulation. How do we get R in? This is something called diode connector. I would not go into details. I will prove it to you. But what is the meaning of diode connector? Please go look at the E124 video I sent you. We have a video talking about diode connector, why this is called diode connector. But basically, it's the gate connected to the drain. Then that is called diode connector. So the R impedance, because it's diode connector, so the input impedance equals to 1 over GM1. That's it. Very easy. So we just need to make GM1 equal to 0.02 Siemens. Then I will get out in 1 equal to 50 ohm. Are you okay with this? Right? You trust me first. I say that if you know that already, looking into a diode connected transistor, the input impedance, the impedance is 1 over GM1. Okay, trust me this first. Then if I want to get 50 ohm, I just make the GM1 equal to 0.02 Siemens. How do you achieve a certain GM? Well, what can you do as a circuit designer? We talked about that earlier. Say again. Gate voltage, yeah, which is control the drain current. Yes. And since touch, and what else can you do besides the gate voltage? Yeah, but drain currents. But what else? In terms of your design, channel length and what else? Length and what? Width. Yeah, very good. So you change the width, change the length, and you change the gate voltage biasing. That's again, if in your design you want to get 50 ohm, do something to achieve this, right? Let me quickly show diode connector equation, right? Z in of diode connector. Transistor. The first thing I want to do is what? So let me show you what is the diode connector one more time. This is the circuit, right? And I want to look at this. Am I right? Very ugly drawing, but do you see what I'm drawing? Do you agree? This is diode connector. Gate connected to the drain, looking down. What do you do? Small signal. Draw this guy. This is plus minus VGS. I ignore channel length modulation, so no out. What is this? GM VGS. That's it, right? Then I need to connect them, correct? The gate is connected to the drain through RF, right? And what I'm looking at is this point. This is Z in, and this is grounded. So I need to solve the KCL and KVL for this one, Vx and Ix. What is Ix? What is Ix in this point? And what is Vx? So the Z in, let me use green, equals to Vx divided by Ix. But Vx is just equal to VGS. Do you agree? Just VG. Vx is this point, equal to Vg. Do you agree? Isn't there if RF, Y is equal to Vg? Is there any potential drop across the RF? This point is Vx. This point is Vg. Why Vx equal to Vg? Because there's no current. This is open. No current can flow. Right? So yeah, Vx equal to I times RF. Vg equal to Vx minus RF times I, by I is 0. So this is just equal to Vg. Right? So let me emphasize here. This is 0. Okay. And what is Ix? Where does they go? GM VGS, right? GM VGS. So what is this? 1 over GM. Okay? Right? So you either memorize it, either you can prove it so fast. Diode connector 1 over GM. If you claim that you are an analog circuit designer, this is a fundamental, right? Just like those physics people ask you what's the speed of light, you should be able to say it, right? If no, you cannot claim that you have a degree in physics. Same for analog circuit designer, right? What is the input impedance of a diode connected transistor? 1 over GM. Right? Of course, there are many details. 1 over GM parallel R0 if you have channel length modulation. You can say many things if you have body effect. Fine. But no one requires you to memorize this. This is the feeling. The feeling you show people. You have this intuition that other people do not have. Okay? So 1 over GM. And that is the good thing. I did not add any resistor. I add RF, but we're going to show you that RF has very small contribution to the noise. Okay, so let's talk about the gain of this circuit. What is the gain of this circuit? This time we need to be careful because we're talking about the gain. We need to consider the RS, okay? So what is the gain of the circuit by definition? A V equal to what by definition? Someone tell me. V out over V in. Very good. But we don't know what it is by looking at this. We're going to do step by step. I call this part X. So of course equal to V out over Vx and then times Vx over V in, right? Step by step. Why do I do this? I do this just because I already have the equation for that. Because Vx has nothing to do with Rf. And when Rf is large, I can ignore it, okay? So I'm going to assume very large RF, like infinity. It's just that you don't have RF, right? So in that case, what is the gain of the second part? No, V out divided by Vx. What is the gain of the second part? This is the gain of what? Or of which type of circuit? Huh? Common source amplifier. And you check your cheat sheet. It is negative GM1. And then now this is a little bit. Did I say something wrong? The opposite. Yeah, so sorry, I did not follow my cheat sheet, so I cannot do this. I cannot assume very large RF. I'm sorry for that. Right, so my goal is to say that this is GM1 and then times R1, R01 parallel R2, right? So I cannot do this. I cannot ignore it. I'm sorry for that. I cannot ignore RF by saying that it is very large because that is not the case in our operation. Okay, so then what can we do? I mean, all we can do is just to go through the KCL, KVL. Okay, so I will start with this. Look at the current. Vx minus V out divided by Rf. Vx minus V out divided by Rf. If my assumption were correct, this is 0, very large RF, right? But now it is not correct, so I'm sorry for that. Equals to what? Equals to Ix. Maybe I should just call this Ix. I'm going to call. Is that okay? It's the current going through, right? It's just equal to Vx. Because all the current will go through here, just like what you told me earlier, remember? Is that okay? Sorry I confused you, but what I'm trying to do now is to look at the KCL. Current going through here will be going to here, which is Vx minus V out divided by Rf, which is the Ohm's law. Okay? But what is Ix? This Ix also go to here. Right? Not just Ix, I mean, this also, I should say another equation. This gives me one equation, right? And then I have second equation, which is Vx minus V out divided by Rf. Where does this current go? If you look at the small signal, they all go to here. Maybe I make this clearer, right? This is Ix. This is Vx minus V out divided by Rf. And then you have this current, which is GmVx. So that's why I put this as GmVx. Okay, let me step back a little bit, right? So what I'm trying to do, I look at here, maybe some of you cannot see it because this is a current source, it's completely gone, right? I told you earlier, it's small signal. So the current Ix comes to here, and then it becomes this current is Vx minus Vout divided by Rf. And then it becomes this current, it's clear to see here. This is ID. I asked you earlier, what is this? GM Vx, right? GM VGA. Is that okay? So this one gives me this equation. I group the Vx together. I have Vx equals to Vout plus GM Vx Rf. I have not grouped it actually. GM Vx Rf, right? Which means Vout divided by Vx equals to what? 1 minus GM Rf. Right? Because I just need to group this to here and divided by Vx, then I have 1 minus GM Rf. Right? This is from equation 2. But there's one thing very important. This is something I always overlook, and you need to be careful to help you to make things simple. What is the relationship between, of course we have GM, but I want to make it simpler. What is the value of GM now? If impedance match. Remember when we make it match, what happened to GM? Maybe you forgot. You make 1 over GM equals to Rs, 50 ohm, right? So when you make it match, then we have GM equals to 1 over Rs, because we do the impedance matching, right? So as a result, we have Vout Vx equals to 1 minus Rf divided by Rs. That's the first thing we got. Is that okay? So any questions about this? Now, then we are done with this part. This is red part. Right? How about Vx divided by Vin? What is Vx divided by Vin? We are talking about what is the voltage at this point divided by this point. It is just potential divider effect. If we know what is the effective Rin divided by Rin plus Rs. Right? Do you agree? Then how about the capacitor? I say again? Don't care. Why we don't care? Because it only it only useful at DC. Yes, because at the frequency we are operating, we choose a capacitor that is large enough that we don't care, right? When it's large enough, your impedance 1 over omega c, right? So this becomes 0, right? So very good. But what is Vin again in this case if impedance is matching? Huh? When the impedance is matching, Rin equal to what? Rs. Exactly. Equal to 1 over 2. Okay? Which, let me emphasize, Cin matched. Right? So now Cin is Rs, is also 1 over Gm, like what we're saying here, right? So then finally, what is the gain? AV equals to V0 divided by V in equals to half 1 minus RF minus divided by RS. That is the gain. Okay? Now, we also can think about RF is going to be large, right? So if RF much larger than RS, then what do we get? We ignore 1, right? 1 minus a very large number, right? It's just negative RF divided by 2 RS. Okay? How can you make the gain large? How can you make this large? Make RF large. RS smaller is good, but probably you have no control because that is the system given by your boss. We need to, fulfill certain requirement. To interact with our customer's chip. 50 ohm. Make RF very large. Is RF affecting your headroom? No. So unlike the resistive loading, you increase the RD, your gain is larger, but headroom is smaller, right? But now this one, you can have a larger gain, but you don't have a trade-off between them. So you have the decouple the requirements. Okay? Yeah, sorry my cheat sheet is messy, and it turned out I also don't need this equation. I'm sorry for that. Yeah, so I know it's messy, but after all, our goal is what? I just want to find the gain. And why do I need the gain when I'm talking about noise later? Why do you need the gain of an amplifier? To get the noise factor, exactly. So we are paving the road to there, right? And to find this gain, I chop into 2 parts. One is from here to here. I know it's impedance matching. So you see that when you realize it's impedance match, then you simplify many things. Okay, so if you keep the GM here, keep the R in here, the whole thing is very messy, right? With impedance match, then you got this one. Okay. Okay, so let's move forward. We want to do the noise, right? So my question, what is the noise due to RF? We cannot do much. All we need to do just draw the circuit unless you can see it right away, right? So to do the noise, of course, I need to short the inputs. I have the RS here, right? Again, we're doing AC, right? And superposition, so we will short other signal one by one. I have the transistor here. This going to ground. And then, of course, this go to V out. I will go up, but now it's small signal, so the current source is open, so I don't go up. I definitely have a RF here. But I want to study the noise due to RF, so I need to add a noise source. What is the value of this noise source? What is this? Due to RF, what is that? Vn squared, what is that? Someone tell me. 4kTRF. Very good. Right? So my goal is to figure out how this is affecting my output. Looks like I need to, how this become the output noise. So I need to solve KCL, KVL, looks like, right? So let me just, if you cannot see it, then let's just draw the small signal. So this is the gate, right? So plus minus VGS. This is the drain to source, GM VGS. And now you say, okay, this guy is connected to RS and then to ground. And then this one, I have this RF, right? And then I have this noise source, which is 4kTRF. Do you agree with the drawing as the small signal model? Now you can do many things. You can solve KCL, KVL, but here I'm going to do this. What is VGS? VGS is this 2 point, right? So I will say VGS VGS equals to, or let's use Ohm's law, that may make it easier for you. IRS. So if this is IRS, okay, the current going from left to right, right? Then, of course, then VGS, 0 minus VGS divided by RS equals to IRS. Is that okay? 0 minus VGS, but this point is VGS, equals to IRS, divided by RS equal to IRS, right? So this one gives me what? It tells me that VGS equals to negative RS times IRS. Okay? But what is IRS? IRS also equals to GM-VGS. Because this IRS goes here, you have no way to go, right? So I'm saying that we can do this. Then we have VGS times 1 plus RSGM equals to 0. Something times something equal to 0. Can this one be 0? RS is just a real resistance, 50 ohm, right? You cannot say negative, right? GM, positive. Something times something equal to 0, what does it mean? It means VGS must be 0. So good. Then it means this point is 0, right? So if this point is 0, then your output voltage by itself is already at this point. Then you have V and maybe did I do something wrong here? Oh, square will be equals to 4kT RF. I mean, when VGS equals 0, I forgot to set, it also mean what? GM VGS equal to 0. It means all the current equal to 0, right? Basically, this is 0. Then it means this one is 0, right? So no current. So no potential drop. Then I only have a voltage connected to the ground. And that's why the output is just equal to 4kT RF. Now this, I suddenly got confused also. Do you see what I'm trying to do? All we have proof is just that no current flowing through here. And because no current flowing through, you put a voltage source here. This potential from this point to this point must be equal to the voltage source. Make sense? So that's why it's 4kT RF. Any questions? Slow. Okay. Okay, so let's do a little bit faster. Still 2 minutes. I want to finish this slide also. Okay, so now how about the noise coming from the transistor? Let's just draw the circuit again. The noise coming from the transistor I have RS, right? I have this one, and then I have RF, and coming to here, right? The easiest way to incorporate the noise for this circuit is consider this drain to source to the thermal noise in here, which is IN squared equals to 4KT gamma GM, right? That is the noise due to this transistor, right? We ignore the gate thermal noise, resistance noise. We ignore the flicker noise. Then we only have this noise. And to find the equivalent voltage source, all I need is to find the output impedance. Correct? Which is this one. I need to find this. We are D out. Then I will have V out N square equals to what? 4KT gamma GM times Z out square. Right? Right? Because I know I have this current. I just need to multiply current by the impedance, then it will tell me what is the voltage here, right? So my goal is to find out the output impedance. So this one, give me 2 more minutes, okay? I will go to draw the small signal model. How do I do it? Just like what we did earlier. Now I'm going to be faster. RF connected to the gate and the source. And then this is GM, VGS, right? But here is V out, I out, that I want to find the output impedance. And here I have RS, and this is VGS, right? So what is I out? I out, of course, equal to GM VGS plus V0 divided by RS plus RF. Right? Because this current is GM VGS plus the current going through here. So it's V out divided by RS plus RF. Yeah? So because of this, then we have also the current V out divided by RS plus RF. Sorry. Which is the current, right? Times RS equal to VGS. This is the first, this is second. So what I'm saying is this. V out, this is just equal to I out, right? This is just I out. This current, which is, no, not I out, sorry. What I'm talking about is this current going through here is V out divided by RS plus RF, right? This current times RS give me VGS. Is that okay? So with this, then I'm going to solve it. I say I out equals to GM. I'm going to plug in VGS, which is V out divided by RS plus RF, right, times RS plus V out divided by RS plus RF. Right, what I'm doing is I plug in this. I have this first equation, I out equal to the whole thing. So GM times VGS, I just put this whole thing as VGS and just copy this whole thing here. And now I eliminate other variables. So I get V out divided by I out. If you go through the math, equals to RS plus RF divided by 1 plus GM RS. But GM, 1 over GM equals to RS. So what is this? This gives me 2. So the whole thing is just RF plus RS divided by 2. That is the output impedance. Then we multiply this one to here to get the noise. Okay? Sorry for doing this. So I will repeat again on Wednesday. Okay? Thank you. It's too late.